Assalamu alaikum. My name is Saad Ashraf and I will be explaining 2-3 tree. A 2-3 tree is a multi-way search tree. It is a self-balancing tree. It has following characteristics. A node contains one or two keys. Every internal node has either two children if it contains one key or three children if it contains two keys. All leaves are at the same level in the tree, so the tree is always height balanced. The search property of 2-3 tree is similar to binary search tree. Each node of 2-3 tree has one or two keys. For the node that has single key, its left subtree has smaller values and its right subtree has greater values. For the node that has two keys, it has three child subtrees. The left subtree has values that are smaller than first key of parent node. The middle subtree has values that lies in between the first and second key of the parent node. And the right subtree has values that are greater than second key of the parent. 2-3 search tree has some special steps during insertion and deletion that ensure their structure remains the same. Searching for a value in a 2-3 tree is similar to search in a binary search tree. We will try to search value 5 in this tree. We will begin our search from the root node. 5 is not present in the root node. Now 5 is greater than 2 and less than 9, so we will proceed to the middle subtree. Since node does not have 5 and it does not have the child node, so we will conclude that 5 is not present in the tree. Insertion in 2-3 tree. The first step of the insertion is to find the right node where the record has to be inserted. If the node contains only one value, then it can easily be inserted. Otherwise, after insertion, the value the node has to be split up, and this is explained by the following examples. We will insert key 14 into this tree. The value is first compared against the root node. Since 14 is less than the left value of the root node, the left child node is followed next. This node has only one element and 14 is greater than 12, so the center child is followed next. We have reached a leaf node. Since leaf node has an empty space, so value 14 can be inserted into the node. But before inserting, 15 needs to be shifted to the right to make space for the new key. Now the key 14 can be inserted into the tree. The insertion is complete now. Now what will happen if we have to insert a value into a leaf node that already has two keys? Then more space must be created. This is called promotion. The promoted key is then inserted into the parent. If the parent currently contains only one record and thus has only two children, then the promoted record is simply added to the parent node. If the parent is full, then the split and promote process is repeated. Here is an example of simple promotion. Let's assume that we want to insert key 55 into this tree. The key is first compared against the root node. Since 55 is more than the right key of the root node, the right child node is followed. This node has only one element, and 55 is greater than 48, so the center child is followed next. We have reached a leaf node. Since it does not have empty space, so we have to split the node. Now we have to rearrange the keys. At first, the largest key, 55, will go into the new node. Key 50 will stay in its own place. The middle key 52 will be promoted as parent node has some space available. The pointers will now be updated. The insertion is complete now. Assalamu alaikum. My name is Saad Ashraf and I will be explaining Scapegoat Tree. A scapegoat tree is a self-balancing binary search tree. The naming convention of this tree is taken from the idea that when something goes wrong, the first thing we tend to do is find someone to blame, and this is known as scapegoat. So this tree is different from avial tree as it does not use small step-by-step rebalancing operations, but scapegoat trees rarely choose a scapegoat, and this is quite expensive process, and completely rebuilds the subtree rooted at the scapegoat into a complete binary tree. Unlike other self-balancing binary search trees, scapegoat tree doesn't require extra space per node. For example, red-black tree in red-black tree nodes are required to have color. It has big O log of n lookup time, and it also has big O log of n amortized insertion and deletion time. A binary search tree is said to be weight balanced if half of the nodes are on the left of the root and half on the right. An alpha weight balanced node has a relaxed weight balance criteria, and that can be seen in the slide. Size of the left subtree should be less than alpha times size of the node, and size of the right subtree should be less than or equal to alpha times size of the node. Now the question arises about the value of alpha. Basically, an alpha can have any value between 0.5 to 1. Even a degenerate tree that is basically a linked list satisfies this condition, with alpha having the value of 1, whereas an alpha having the value of 0.5 would only match a complete binary tree. The value of alpha can be decided based on the requirement, as a high alpha value results in fewer balances and it makes insertion quicker but searching and deletion slower. A binary search tree is alpha weight balanced, must also be alpha height balanced, that is, height of tree should be less than log to the base inverse of alpha of size of tree. Violation of this height balance condition can be detected at insertion time, and this implies that a violation of the weight balance condition must exist. This makes scapegoat trees similar to red-black trees in that they both have restriction on their height. What does rebuilding the subtree mean? In rebuilding, we simply convert the subtree to the most possible binary search tree. We first store in-order traversal of binary search tree in an array. Then we build a new binary search tree from array by recursively dividing into two halves. The summary of the process of rebuilding can be seen in this image. So now we will look at an example that illustrates insertion. A scapegoat tree with 10 nodes and height 5 can be seen in this image. Let's insert 3.5 in this scapegoat tree. As you can see that before insertion, depth of this scapegoat tree is 5. After insertion, the depth becomes 6. Now the size of the tree is 11. And we know that the value of alpha is 2 by 3. So according to the formula given above, our height should be less than 5.913. Since it is not, so we have to find the scapegoat in order to solve the problem of exceeding height. Now we find a scapegoat. We start with newly added node 3.5 and check whether size of node 3.5 and size of node 3 and the ratio is greater than 2 by 3 or not. Since size of node 3.5 is 1 and size of node 3 is 2, so if we take the ratio size of node 3.5 by size of node 3, that equals in 1 by 2, which is less than 2 by 3. So this is not scapegoat and we move up. Since 3 is not the scapegoat, we move and check the same condition for node 4. Since size of node 3 is equal to 2 and size of node 4 is equal to 3. So size of node 3 by size of node 4 results in 2 by 3, which is not greater than 2 by 3. So this is not the scapegoat and we move up. Now size of node 4 by size of node 2 results in 3 by 6. Since size of node 4 is 3 and size of node 2 is 6, but 3 by 6 is still less than 2 by 3, which does not fulfill the condition of scapegoat. So we again move up. Now size of node 2 and size of node 5 results in 6 by 7. Since size of node 2 is 6 and size of node 5 is 7, 6 by 7 is greater than 2 by 3, which fulfills the condition of scapegoat. So we stop here and hence node 5 is a scapegoat. Finally, after finding the scapegoat, rebuilding process will be taken at the subtree rooted at scapegoat, that is at 5, and finally final tree will be obtained. Assalamu alaikum. My name is Saad Ashraf and I will be explaining Splay tree. Splay tree is another variant of a binary search tree. In Splay tree, recently accessed element is placed at the root of the tree. We can define a Splay tree as a self-adjusted binary search tree in which every operation on element rearranges the tree so that the element is placed at the root position of the tree. All the operations in Splay tree are involved with a common operation called splaying. The search operation in Splay tree is same as searching the element in binary search tree, but afterwards the searched element is splayed, which means that it is placed at the root of the tree. So now the question arises that what is Splay tree? Splaying an element is the process of bringing the element to the root position by performing suitable rotation operations. By splaying elements, we basically bring more frequently used elements closer to the root of the tree, so that any operation on those elements is performed quickly. Every operation on Splay tree involves the splaying operation. For example, the insertion operation first inserts the new element using the binary search tree's insertion process. Then the newly inserted element is splayed so that it is placed at the root of the tree. Now we will look at the insertion operation in Splay tree. At first we will check whether tree is empty or not. If tree is empty, then we will insert the new node as root node and exit from the operation. And if tree is not empty, then we will insert the new node as leaf node using binary search tree insertion logic. After insertion, we will splay the new node. To splay any element, there are 6 rotations. We have zig rotation, zag rotation, zigzag rotation, zag-zag rotation, zigzag rotation, and zag-zag rotation. Zig rotation is similar to the single right rotation of avial tree. In this rotation, every node moves one position to the right from its current position, as it can be seen in the slide. We are basically splaying node with value 3. In this process, the right child of node 3 is adjusted by becoming the left child of node 5. The zag rotation is quite similar to the single rotation of avial tree. In this rotation, every node moves one position to the left from its current position, as it can be seen in this image. The zig-zag rotation in Splay tree is basically a double zig rotation. In this rotation, every node moves two positions to the right from its current position, as it can be seen in the slide. The zag-zag rotation in Splay tree is a double zag rotation. In this rotation, every node moves two positions to the left from its current position. This can also be seen in the slide. Zigzag rotation is basically zig rotation followed by zag rotation. In this rotation, every node moves one position to the right, followed by one position to the left from its current position, as it can be seen in the slide. The zag-zig rotation in Splay tree is basically a zag rotation followed by zig rotation. In zag-zig rotation, every node moves one position to the left followed by one position to the right from its current position. This can also be seen in this slide. Assalamu alaikum. My name is Saad Ashraf and I will be explaining T-tree. T-tree is a type of binary tree data structure that is used by main memory databases. T-tree is basically optimized for cases where we need to store both the index and the actual data in memory. T-trees do not keep copies of the index data fields. Instead, they contain the actual data. They take advantage of the fact that the actual data is always in main memory together with the index, so that they just contain pointers to the actual data fields. So now we will look at the basic structure. A T-tree node usually consists of pointers to the parent node, the left and right child node as it can be seen in this image, and an ordered array of data pointers and some control data. Now we will look at terminology of T-tree. Nodes with two subtrees are called internal nodes. Nodes without subtrees are called leaf nodes, and nodes with only one subtree are called half-leaf nodes. A node is called bounding node for a value if the value is between the node's current minimum and maximum value. In internal node of the T-tree, we have greatest lower bound. This value is slightly smaller than the smallest data in the node. More appropriately, we can say that greatest lower bound will be predecessor to the smallest value in the node. We also have least upper bound, and this value is successor to the largest value in the node. Each internal node have predefined number of minimum and maximum number of elements. The process of searching begins at the root node. We will check the minimum and maximum values of the node, and if the search value lies in between these values, Then we will continue to search each value in the data array. Now the value will be returned if it is found, or null will be returned if it does not exist. Now what will happen if the search value does not lie in between the minimum and maximum bounding value? We will proceed to the left subtree if the search value is smaller than the range, and if the search value is greater than the range, we will proceed to the right subtree. Search will fail if the right or left subtree is not present. Thank you.